Last month, Bobby Shafto released this video of the USS Zumwalt with part of its hull hidden by the horizon. And he was hoping that a flat earther could explain how this bottom-up disappearing occurs due to the conversion compression effects of perspective and angular resolution limits, and is not due to curvature. So Flat Earth Perth replied with this comment: "Hey Bobby, I have filmed similar many times. The answer is simple: waves. And if you're like me, you're probably looking at this photograph and thinking, what waves?" So this is another comment that starts off: "For the Globers who don't understand what our oceans actually are," listing things to back up his claim that the waves are hiding the hull of that ship. So is this real science or more flatter pseudoscience? So first, let's take a look at the type of waves we would typically see in these videos. And I'm going to start with wind waves. So on the left, these waves are under 2 feet. And I know this because white caps will start to form at about 2 feet. So when you start seeing scattered white caps like in these two center photographs, you know the waves are at least 2 to 3 feet in size. And then when you look over on the right over here and you see a lot of white caps, now we're starting to get into some very large wind waves. And then we have swells that are typically caused by distant storms, and they have enough energy to travel long distances across the ocean. So 3 of the characteristics is they travel in parallel lines, the wavelength is long, and they have a rounded crest. Now these are easy to see here because they are shoaling. They're entering shallow water, so they're going to reach their highest height. And you can also see that these are the favored amongst surfers. But if you look up here to the upper right, they are quite difficult to see. So let's watch Bobby's video and keep these 2 questions here in mind. Now there are no visible whitecaps, so we know the wind waves are small. And look at the waves on the horizon. Even the combination of wind waves and swells is small. So why would anyone bring waves into this debate? Now it looks like there's a thin inferior mirage because the bow of the boat right here bends under. But look how thin the combination of that mirage and waves are. How could that possibly hide what is missing of this ship's hull? So this is a photograph of the Zumwalt, and you can tell that it is a big ship by looking at the tugboats. It is 600 feet long, and I've done my best to scale it to the silhouette in Bobby's video. So here's the silhouette again. Now we have a good estimation of the ship's waterline. Now I did find a website that compared the flight deck of the Zumwalt to another Navy vessel. So the freeboard, or the height of the hull above the water, is 22 feet or 6.7 meters. So we can see that the top of the flight deck is aligned with the horizon. So 22 feet or 6.7 meters is a good estimation of how much of the hull we do not see. So let's see how Flat Earth Perth tries to explain this away with waves. So first he says, use significant wave height. So let's go to his link. So this is from the Australian Government Bureau of Meteorology, and it's really a good website to help people estimate how big of waves they might see on the sea. It includes these 2 charts, so let's take a look at these. Now, if you've ever spent any time on the water, you know that waves are not of a constant height. So this is a graph showing the typical distribution of waves that you would see on a normal day. So the significant wave is an average of the largest third of all waves. It includes both wind waves and swells, and is data that is typically collected by buoys. Up here we have the maximum wave height, or that is a wave that is twice the height of a significant wave and is likely to occur 3 times in 24 hours. And then down here we have the most frequent wave height. Now there are other websites that include these math calculations that give you a better idea of what these wave sizes will actually be. And they're all based on the significant wave height. And I'm going to use 4 meters since Flat Earth Perth talks about a 4-meter wave. So for the most frequent wave down here, you would multiply 0.6 times the significant wave height, and in this case it would be 2.4 meters. Up here we have H1/10, that would be 5.1 meters, and that would be 1 in every 10 waves. Up here we have H1/100th, and that would be 6.68 meters. That would be 1 in every 100 waves. And then of course we have H max, which is the maximum wave height, and that would be 8 meters. So again, this would be the distribution of the waves. So 2/3 of the waves are going to be down here. Some of them will be bigger than 2.4 meters, some of them will be smaller. And then 1/3 of the waves are going to be in this size. And then of course, we have the maximum wave height that you might see 3 times in 24 hours. So this is the other chart from the Australian government. It says basically the same thing. The most frequent wave height will be about half the height of the significant wave. About 14% of waves, or 1 in every 7 waves, will be higher than the significant wave height. And then it is normal to expect a wave of twice the height of the significant wave, about 3 times in 24 hours. And again, this is really good information. So next he says, understand the wave height variations that occur every day. At time of post, I found wave heights from 1.8 right up to 15 meters. So let's take a look at this website. So this is the Earth Null School website, and this one here is an interactive color-coded map for wave sizes around the world. They go from a low in the blue area here all the way up to the high in the red area down here. These are just 3 locations that I picked out. Now this is a very fascinating website. They also have one for wind, but I'm really not certain what this has to do with Bobby Shafto's video. Number 3, understand that if the significant wave height is, say, 4 meters between the observer and the ship, wait for it, listen carefully, are you ready? Regardless of the observer height, let's say 7 meters, if the ship is 13 miles away, then at least 4 meters of the ship will be obstructed. If you don't agree, look at the permalink below. So we set this up on Walter Bislin's website, and he used these objects to represent 4-meter waves. Now, if this was a pier and that ship was docked at the pier, I would agree with Flat Earth Perth 100%. But we are talking about waves, so there's 2 major problems with this. First of all, waves have a crest and they have a trough, and calm sea level is right in between the 2. So a 4-meter wave is only going to be 2 meters higher than calm sea level, not 4 meters higher. The other thing is that since boats float on water, they interact with large waves. Here you can see this boat going down into a trough and you can barely see the hull. Now it's rising up on a crest and you can see all of the hull. We certainly don't see this happening in Bobby Shafto's video. So sorry to be blunt, but this is wrong. 4, understand that the maximum wave height can be 3 times the size of the significant wave height. So the 4-meter waves can become 12-meter waves every now and then. Point being that when Globers say things like, oh yeah, waves, that's ridiculous, I chuckle because that's pure ignorance. Well, I'm sorry, because not only does your source say that the maximum wave height would be twice the height of a significant wave, you made no mention of the fact that the most frequent wave height will be about half the height of the significant wave. So again, this statement is wrong. What is the significant wave height for that footage? We don't know, so next time research that and include the details. Now, Bobby did not include that in the video or his description, but he did tell Flat Earth Perth in a comment. So offshore buoy swell data on that day and time was 0.66 meters. So this is the distribution of waves using 0.66 as a significant wave height. Most of the waves are going to be down here, 0.4 meters. That's less than 1.5 feet. 1 in every 10 waves, 0.84 meters, 1 in every 100 waves, 1.1 meter, and then maybe 3 times in 24 hours, 1.32 meters. And did we really need that data to understand that these waves are not that big? When you have waves up in the 4-meter range, you're going to see something like this. Well, I'm going to stop here because I think I've shown that Flat Earth Perth really doesn't know as much about waves as he thinks he does. He does continue on, but to be honest, about the only argument he did not use was that that ship's hull was being hidden by kitchen sinks. But at the very end, he did say, I propose that Glover stop getting triggered by words like waves or perspective and start researching the facts so we can acknowledge some common ground. And I find this sentence quite interesting considering how he twisted the facts to fit his agenda. But before we go, let's do one last thing and compare this photo to the curvature calculator. So the distance is 13 miles, viewer height is 25 feet, that gives us 23.3 feet of refracted hidden and 31.5 feet of geometric hidden. So the horizon is hiding about 22 feet of that ship. So let's take a look at the air rates for the globe model. The globe refracted hidden was 23.3 feet minus 22 feet. That's a difference of 1.3 feet. I mean, that is a really good match with what we see in Bobby Shafto's video. The globe geometric hidden was 31.5 feet minus 22 feet. That is a difference of 9.5 feet. So let's take a look at the flat Earth model. Now we know that a flat surface is not an obstruction, so the flat Earth hidden would be 0 feet. That means a difference of 22 feet. So the flat Earth model comes in dead last. So I think we know why Flat Earth Perth came up with his fantasy 4-meter waves to try to explain this away.